Hello and welcome to another episode of Literature Talk. Today we are delighted to have with us Angshuman Roy. He completed his MSc from Rajabazar Science College, Calcutta University, and is currently second year PhD student in the Department of Organic Chemistry at IIC Bangalore. In today's presentation, he'll be discussing an exciting and rapidly growing area of research, single atom catalyst and their applications in organic synthesis. So Angshuman, welcome to the talk and the screen is yours.
Thank you, Bhaiya, for your kind introduction. Welcome again, another lecture series of Turning Point. So, today's topic of discussion is single atom catalyst and its application in organic synthesis. So, before going to the main discussion, I will give a brief overview of the discussion. So, first I will discuss the introduction part, then I will move towards the historical development of single atom catalyst. After that, I will discuss some of the preparation method of single atom catalyst. Then I will discuss the application of single atom catalysts in organic synthesis. After that, I will conclude my lecture with future outlook and conclusion. So, as we all know that catalyst lies in the very heart of chemistry, from large-scale industrial process to small organic reactions. Large-scale industrial process like ammonia production, methanol synthesis, and other industrial process which involve catalyst at some stage, and this process demands high energy efficiency optimization or uh, energy optimization as well as uh, high efficiency. Further, moving to fine chemical and pharmaceutical industry, the catalyst based drug synthesis as well as asymmetric synthesis, selective oxidation reductions are important. Catalysts also have waste reduction and reuse application like CO2 utilization, converting pollutants into valuable products, etc. It has environmental application also like green sustainable reactions like water gas splitting reaction for hydrogen production, etc. So broadly, catalysts actually divided into two parts like homogeneous catalyst and heterogeneous catalyst. Homogeneous catalyst actually operates as the same phase like as reactant, which shows highly selectivity as well as reactivity because of their uniform active site. Despite of their excellent activity and selectivity, it has some several limitations like poor recyclability as well as moisture, air sensitive, etc. On the other hand, heterogeneous catalyst is stable, easily separable as well as not moisture, air sensitive, but it also has some limitations like lower selectivity. So this limitation of traditional catalyst lead to develop one new catalyst which is known as single atom catalyst. So single atom catalyst actually aim to combine the advantages of both heterogeneous both heterogeneous catalyst as well as homogeneous catalyst, which it provide limited metal loading, uniform active site, easy to recyclable as well as it provide better stability. So the single atom catalyst actually basically the single metal atom is atomically dispersed throughout the solid support. So this idea that single atom can act as catalyst, this is not entirely new. As early as 1970, the Cope et al. First demonstrate that nickel palladium single atom dispersed on a carbon film can act as a catalyst, and they use this catalyst for methane production reaction. This is the first example where they showed that catalyst single metal atom can act as a catalyst. So despite their serendipitous finding, the scientific community actually overlooked their work because of the experimental challenges of visualization of atomically dispersed site with microscope. A major breakthrough came in 2011 when Zhang group first developed a platinum dispersed on an iron oxide nanoseed, which they used this catalyst for carbon monoxide oxidation reaction, and this catalyst shows exponentially high catalytic performance. This same image where we can see that these white dots are representing the platinum single atom which dispersed throughout the iron oxide nanosheet. Now, in 2013, Lin et al. Reported a technique which is known as atomic layer deposition technique, and they made iridium single atom disperse on iron oxide nanosheet, and they use this catalyst for water gas split reaction where the catalyst shows high performance. This is the STM image of iridium single atom catalyst. Now, in 2015, Remais et al. Discovered the palladium single atom catalyst, where the palladium atom is dispersed in graphene nitride, and they use this catalyst for hydrogenation reaction. But they shows that this catalyst showing a very good performance compared to the traditional palladium nano catalyst. Now, in 2016, one group stabilized the rhodium single atom on zinc oxide nanowire, and they use this catalyst for olefin hydroformylation reaction, where this catalyst shows homogeneous like efficiency with maintaining heterogeneous like recyclability as well as stability. In present day, in catalysis field, this research domain shows an excellent growth in between 2014 to 2024. The single atom catalyst actually focused on the diverse field like organic transformation, hydroformylation, oxidation, as well as large industrial processes also. Before going to its application, so I will discuss some of the preparation method of single atom catalyst. So the synthesis method actually divided into two broad categories. First of all is top-down approach, where we can first of all is the top-down approach, where it involves energy-related method to crush and break down large metal particles such as in individual isolated metal atoms without affecting the structural support. Pyrolysis method, photochemical method, and mechanochemical method is the example of top-down approach. In all these cases, the chosen synthetic route always depends on the high energy as well as sophisticated instrumentation technique. On the other hand, bottom-up approach method, which exploits reactions between metal salt and metal precursor, and then the single metal atom atomically dispersed throughout the solid support. The wet chemistry method, atomic layer deposition method, as well as electrochemical synthesis is the example of bottom-up approach method. So due to lack of time, I will discuss the one of the method type synthesis approach from each method type. So for that, first I will start wet chemistry method, which is a basically bottom-up approach method. Here is the idea is basically to immerse metal solid support into the ethanolic or aqueous solution of metal precursor, and the idea is basically to interact metal precursor with the anchoric site present in solid support. Then the collected solution was centrifuged, and the collected solid was undergoing reduction in presence of hydrogen or any other chemical reducing agent is in some elevated temperature, which disperse this metal atom single atom throughout the solid support. So for that, the one group developed a method where they made platinum single atom dispersed on nickel oxide. For the metal precursor, they use hexafluoroplatinic acid, and the solid support they use nickel oxide. So this is the HADF stem image, where we can see these yellow dots are representing the platinum single atom, which is dispersed throughout the nickel oxide support. This elemental mapping confirms that nickel is uniformly distributed throughout the solid support. There is no metal-metal bond formation as well as no cluster formation. Now I'll move towards the another method, which is basically known as pyrolysis process. This is the most versatile method in top-down approach. Here, idea is basically to mix nitrogen-rich ligand which would donate nitrogen, metal salt which is the metal precursor, and solid support like the support material. And the idea is basically to mix this together, and the resultant resultant solution was undergoing pyrolysis at some elevated temperature in between 700,000 degree, which actually dispersed this metal single atom throughout its solid support. So for that, the Zhang et al. Discovered one cobalt single atom synthesis where they used 110 phenol as nitrogen rich ligand, cobalt acetate as metal precursor, and CMK3 which is a carbon nano support. They mixed this together and the resultant mixture was undergoing pyrolysis at 800 degree temperature for 2 hours. This is the cartoonish representation of the cobalt single atom catalyst. These red balls are representing the cobalt single atom which is dispersed throughout the CMK solid support. This is the STM image where we can see these white dots representing the cobalt single atom throughout the CMK support, and this is a backscatter electron image where it is clearly visible that white dots are representing that the cobalt single atom dispersed on the CMK support. Now, so I will discuss some of the example of metal single atom catalyst and inorganic synthesis. So for that, we all know that CN coupling reaction actually basically involve transition metal catalyst, because transition metal catalyst provide highly selectivity as well as the reactivity. Few recent years, the CN coupling with the help of copper catalyst is basically growing. So for that, they use actually copper halide as catalyst because of their cheap as well as easily abundant and less toxic. So despite of its major advantages, it has some limitation like high catalyst loading as well as difficult recovery and poor recyclability. So to overcome these challenges, Zhang group developed one cobalt single atom catalyst where cobalt single atom is dispersed in end-doped graphene system where it produces 100% metal utilization as well as high selectivity and recyclability. So for that, they use for the making of this catalyst, they use actually pyrolysis method, which I discussed earlier. So they use aniline as a nitrogen-rich ligand, copper chloride as a metal salt, and graphene as solid support. After that, the resultant mixture was undergoing reduction in presence of NaBH4, and then the solid was then pyrolyzed at 400 degree Celsius in presence of hydrogen, which produce this cobalt single atom catalyst where cobalt is dispersed in graphene, end of graphene, where this aniline actually acts as a nitrogen source as well as the selecting ligand for copper ion. After making this catalyst, they characterize it. This is the EM image where we can see the wrinkle graphene structure which is presenting that the graphene present in it, but there is no visible copper single atom. This is the HRTM image where we can see this 002 plane representing the graphene. So then they did EDS mapping where we can see that copper is distributed uniformly throughout the graphene support, and there is no cluster formation, there is no copper cluster formation or any nanoparticle formation. And this is the ACHADF stem image where these white dots are representing the copper single atom. So now they actually after characterization, they actually optimize the reaction condition. This is the optimized reaction condition. After that, they check the substrate scope. These are some selected example where we can see this aliphatic amine as well as cyclic amine is well tolerable and producing excellent yield. Now they checked with heterocyclic amine also, which also produce excellent yield. After that, they checked with electron donating as well as electron withdrawing as well as electron donating iodobenzene, which produce excellent yield as well as well tolerable. Now let's come to the mechanism where we can see that first actually this amine get absorbed in the copper metal single atom. Further, the oxidative addition of iodobenzene generates this species. Then the catalytic cycle closes by reductive elevation and producing our desired product as well as regenerating our copper catalyst. So now I will move toward the another example, which is the hydroboration reaction, where they use copper metal single atom catalyst. So for the making of that catalyst, they use actually wet chemistry method, which I earlier discussed. For that, they use copper chloride as metal salt, which is a metal precursor basically, and titanium carbide as solid support. Then they mix this together and the collected solid was undergoing reduction in presence of hydrogen as 100 degrees Celsius for 2 hours, which actually disperse this copper metal single atom throughout the titanium carbide surface. This is the cartoonic representation of the catalyst. After making this catalyst, they characterize it. So this is the TM image of the catalyst, where we can see this wrinkle structure representing the titanium carbide system. And this is the HADF stem image, where we can see these yellow dots are representing the copper single atom dispersed throughout the titanium carbide support. And this is the EDS mapping, where it's confirmed that the presence of copper and titanium, which is uniformly distributed throughout the support. So after characterization, they optimize the reaction condition. This is the optimized reaction condition. When they check for the substrate group, and these are some selected example, or we can see that cyclic alkene as well as aliphatic alkene is well tolerable and producing good yield. The checked is for electron donating as well as electron withdrawing alkene, which also well tolerable and producing more good to moderate yield. Now, heterocyclic alkene is well tolerable and producing good yield. So, coming to the mechanism of hydroboration reaction, where first actually water gets undergoes oxidative addition and producing this species. Then the transmutation occurs, which then produce this species where the bipene is added in the copper center. After that, the coordination of alkene produce this species. Then the migratory insertion produce this species, and the catalytic cycle closes via reactive elevation, which regenerates the copper single atom as well as producing the desired product. Now I'll move towards another example, which is basically carbon insertion reaction, where we know that for carbon insertion reaction, generally rhodium catalyst is used, which produce highly selectivity as well as reactivity. So despite of its major advantages, it has some limitation like high rhodium loading as well as low metal utilization and difficult to recovery. So for that, the Zhao group developed one rhodium single atom catalyst, where rhodium actually dispersed in the zeolite imidazole framework, and this catalyst shows 100% rhodium utilization as well as low catalyst loading, and as well as the recovery of this catalyst is very easy, which produce this catalyst better stability as well as reactivity. So they made this catalyst via pyrolysis method, where basically they heated this zeolite imageal framework and in some elevated temperature like 950 degree, which creates some void in it. After that, the rhodium-3 solution gets adsorbed in it. They use actually rhodium methanolic rhodium chloride solution. After the absorption of rhodium, they carbonize and they actually heated this sample in 250 degree Celsius, where basically the rhodium metal single atom catalyst form. Where you can see this cartoon is representing the rhodium single atom catalyst. So after synthesizing the catalyst it. This is the TM image. This is the STM image where we can see the void of that zeolite immersion framework. This is the EDS mapping where you can see that rhodium is dispersed throughout the zeolite immersion framework. And after that is the HAD STM image. These white dots are representing the rhodium single atom dispersed throughout the zeolite immersion framework. After characterization, they optimize the reaction condition. This is the optimized reaction condition, and then they checked the substrate scope. These are some selected examples where we can see the secondary amine as well as electron donating as well as electron withdrawing amine is well tolerable and producing moderate to good yield. The aliphatic diazoester as well as heterocyclic diazoester is well tolerable and producing moderate yield. So further they did the mechanistic study. This is the mechanism. First of all, the carbon formation occurs where it produces goes by this intermediate, then NH insertion occurs, and this is the transition state for the NH insertion. After that, the reaction Faraday cycle closes and regenerating our catalyst as well as producing our desired product. So now I will discuss some of the future outlook of single atom catalyst. So for that, actually, first we need to first of all we need a scalable as well as cost-effective synthesis method. The focus should be on the developing simple, reproducible, and industrially viable technique that maintain the atomic dispersion at a very high metal loading. Secondly, improving the stability under particular condition is very important. Strong metal-metal bond interaction can help by preventing metal leaching as well as the decomposition of catalyst at high temperature. Finally, the metal single atom catalyst would be expand into complex asymmetric organic transformation as well as cascade reaction. This will help bridge the gap between laboratory research as well as real world application. So that is from my side, and I will conclude my lecture. First of all, I discuss the introduction part, then I discuss some of the historical development of single atom catalyst, then I discuss the preparation method of it. After that, its application in organic synthesis, and I discuss some of the future outlook of a single atom catalyst. So that's all from my side. Thank you everyone for listening.
Nice presentation, Angshuma.
Thank you. Thank you.
If you enjoyed this session, don't forget to like, share, and subscribe. We'll meet you in the next episode, next session. Thanks for watching.